Okay, so last time we were talking about normal distributions and oh, wrong thing here. Getting there. Actually, the easiest thing to do that. Section 5, Tuesday, Thursday. So we'll probably finish up chapter 12 today. The next, oh, I was going to say the test, but there is no test for this one. the project is due next Tuesday. Okay. So you should be able to do. You should have been able to do the computer part, and we were going through how to solve these particular problems last time. So what we're going to do is just do a few more examples. And I'm going to change these slightly just to make them a little more interesting. So so here we have a problem. IQ scores. Okay, shh, time to be quiet. So most everyone has probably taken an IQ test at one time or another. You may not remember it, but all kindergartners have to take an IQ test, and that's used for determining whether somebody should be in a, I guess, either direction, probably gifted program or remedial type thing. And the way that the IQ test is set up is such that the mean value is 100 and the standard deviation is 15. And the results come very close to fitting a normal curve. So we can use the information that we came up with the other day, and I just remembered I have the table. I printed out the table so we can use this in class to just to get used to using it. You'll need to use this for your project. So for you guys online, if you can go to page 671 in your book, you'll see it. But in case somebody didn't bring a book today, so just like we did on Thursday before the break, you know, we typically drew a curve just to show a typical standard distribution. I mean, normal distribution, a standard normal distribution, and looked at the questions and see if we can figure out what they look like graphically. This one, we almost don't even need to show the curve because of the fact that they're just asking for the percentage of people whose IQ scores fall less than 100, with the average being 100, or the mean being 100, and the curve being symmetric. What percent of people have an IQ less than 100? 50%, yeah. So it's 50% just from the fact that that's what the normal curve has. 50% of the data is less than the mean, 50% is greater than the mean. Okay. Now, when they test for the gifted, when they used to test for the gifted program, the cutoff was 125. So let's ask the question, what percentage students have an IQ greater than 125? Because that'll tell us what percentage of students, of the population of students, normally you would get. If you say you have 150 people who are kindergarten students, how many students would you expect to place in the gifted program if you set the limit at 125 for the IQ test? Now that's not the only things that they use to decide whether you're going into the gifted program or not, but this is one of them. So if you have to have at least 125 plus some other stuff, this will give you the maximum number of students you have. So again, if we draw the picture of what this represents, here's our normal curve again with the mean of 100. So we go draw a line straight down here. Here's 100. So 125 is going to be somewhere over here. We don't know exactly where it is, so we'll just, and what we need is greater than 125. So that's the area underneath this little tail part. So when you're doing tails, whether you're doing tail on the lower side or the upper side, you always subtract a value from 0.5, because if we take the table would give us the area from the area underneath the curve from the mean to some z-score. So that's what the table is going to give us. We know from this kind of reasoning that if we take the whole upper half or the whole lower half, that's going to be 50%. So we're going to take 50%, which is everything. We're going to subtract the red, and that'll leave us what's left over, the little black part. So what you would do is you would find the z-score associated with 125. So the z-score is the x value minus the mean divided by the standard deviation. So in this case, our x value is 125. Our mean is 100. And we divide by the standard deviation of 15. So we get my calculator out, see what that is. So 125 minus 100 is 25, divided by 15. You get 1.67 if you round off to 2 digits. So we get a z-score of 1.67. So the next thing we're going to do is we're going to use the table. So go ahead and look in your table for a z-score of 1.67. And remember, this is just one long table, just accordioned. So you're just going to look for the column which has 1.67 in it under the z. Looks like the fourth set of data, fourth set of numbers. And let's see, who am I going to ask? I'm going to ask Eli. So what is the area associated with the z-score of 1.6? Actually, it's the third column, third set of columns. So what is the area associated with a z-score of 1.67? 0.453. Very good. Okay, so the area associated with a z equal to 1.67 is 0.453. So the area that I'm looking for here, which is this black area, is 0.5, which is the area underneath half the curve, minus the area underneath the red curve, and that gives me the tail, the little tail part. So it's 0.5 minus 0.453, which is 0.047, or 4.7% of the students have an IQ greater than 125. So if you had, let's say if you had 150 students in an elementary school per year on average, because it varies from year to year. Some year you have smart kids, some years you don't have as many smart kids. So you'd multiply that by 0.047. So you get 7 students. And that's between, there are currently 3 elementary schools in the county, Allegheny County. So they actually lowered the standard because that's the problem, is that you don't get enough students in your program if you, as your attendance dwindles, and you have somebody who's specifically doing the gifted program. It is? Yeah, well, it must be going down after that, and I just No comment. No, just hesitation says everything. No, just kidding. Yeah, I tell the story. Well, the person in our neighborhood used to be in charge of the gifted program. Now my wife's in charge of the elementary school gifted program, so she does the testing. She does the IQ testing. And but before she was involved, Jennifer was tested, my older daughter, and I remember her stopping. She'd been tested for IQ, and she stopped, and she goes, "We did Jennifer's IQ test. It was really good. It was 150, which is really good." I don't think it was actually. I don't think it's just she's that smart, but she does have a reasonably high IQ. So anyway, that's 150. That's like top 0.0 something percent. Anyway, I've taken the IQ test. I was just curious, after I heard Jennifer had such a high IQ. You can take these ones that you get like a little book. And it's amazing, it varies between when you take the test. Yeah, even taking, yeah. I mean, I've done a few just out of curiosity. I got one that was like 140 and then one that was 120 something. So, that is a variation of. Yeah, yeah. I think that's one reason they've lowered the limit a little bit, just because, it varies from day to day depending upon the kid. And it's interesting too, you get the case where people are what are called, what's it called, double identified. So they have an IQ, but they're autistic. So they're in another, you have two kinds of, two special situations. You're special because of the autism, and you're special because of the gifted nature. So Martha's had a couple of those students, so it's kind of interesting just to think about. There's probably a lot of scientists that were probably a little weird, different. Yeah, there was a guy named what's his name? Cavendish. That's his last name. His parents, he came from some kind of royalty, and not royalty, but he came from a well-off family. He was the person that figured out what the universal gravitational constant was by this very sophisticated measurement for the time. But I think he was agoraphobic. He didn't, he didn't like people. Agoraphobic's more like they don't like to be in crowds. I think, you stay at home, you're kind of a homebody. I don't think he was also had very poor social skills. He'd probably be considered to be Asperger's or something like that nowadays. But because of that, his ability to, I guess because of that disability, he was able to focus on one thing so much with such accuracy that looking back and seeing how accurate a measurement he made of that particular quantity, just it shows that you can have a disability but still do pretty amazing things. Okay, so let's do one more here with the IQ. So let's say between 70 and 130. We'll do something different here. Let's say between 87 and 112. So again, what we're going to do is we're going to draw a curve just to make us think about what we're doing. So we draw a curve, which always looks the same. Looks like a bell. We draw a line straight down from the peak, which is our mean, our mean, which in this case is 100. And we locate 87, which is below 100, and we locate 112, which is above the average, above the mean. And so what we have, if we draw vertical lines and mark this out, remember the table applies from the mean to some value, some z-score, so we have to convert these values to z-scores. But we basically have two areas. We have one that's greater than the mean, one that's less than the mean. But because of symmetry, we can apply the same principles to calculate each of these areas. We're going to use the same table. We're going to get a negative z-score for this, but we'll just take the positive version of it and find the corresponding area. So let's get our table out. Well, first let's calculate the z-score. So I'm going to ask you guys to do this, and I'll ask somebody other than Eli, because he's already had his chance. So we want the z-score associated with 87 and the z-score associated with 112. So go ahead and do those calculations. Remember, it's x minus the average. Remember also the standard deviation. For this case, the mean was 100 and the standard deviation was 15. So it's x minus x bar divided by s. Yeah, the other interesting thing about IQ tests is just the fact that there's a verbal part, which basically, as for elementary school, well, for elementary school kids, it's a verbal, it's vocabulary, and then they have the math is more of a spatial thing where you look for patterns. Yeah, I mean, vocabulary depends a lot on what your environment and if you're readers. And that's, I think, why Jennifer did so well, because she was a big reader, and so that made it so that she was also, she used to play, we used to play this memory game. I don't know if you ever played that. It's with the cards, and they have two animals, you know, like 2 zebras and 2 giraffes and lions, and you put them upside down on a table, and then you pick up 2, and then you see if they match, and if they don't, you put them down. You have to remember it. And she was a killer on that thing. She used to yeah. So so I think that probably, I think she just has the skills that worked well with that particular test. It wasn't she was like some crazy genius or whatever. Okay, so Kristen, what'd you get for the z-score associated with 87? So we're not looking for the area yet. We're just looking for the z-score. Yeah. Should be negative something. Negative 13. Should be a number between -3 and 0, most likely. So let's see where you went wrong. Well, you got -13. That's the numerator, but the denominator is 15. In the previous problem, the standard deviation was 1, but it's not always 1. In this case, it's 15. So take 13 and divide by 15, or -13. So -13 divided by 15 is, okay, so it's -0.866, which I'll round up to 0.87. Okay. So Josh, what did you get for a z-score of 112? Okay, let's go ahead and do that one. Should be very close, because this is -13. This is going to be +12. You're not sure what to do? Okay. So what is the value? It's 112. What's the mean? 100. Yep. And what's the standard deviation? 15. So you get 12 divided by 15, which is, you have to use your calculator for that. It's good. 0.8. Yep, that's right. It's exactly 0.8. So those are the z-scores. Now what you need to do is go with those z-scores to the table So find the area associated with the z. And what we do is we use the positive, not the negative. So if it's a negative, we're going to use positive 0.87. And we also need the area for a z-score of 0.80. So yeah, let me give you one because I was going to ask you, but you don't have one of those. So Tucker, what you get? What's the area associated with 0.87? 0.308. Let's see if that's right. Yep. So it's 0.308. And Tanner, what's the z-score? What's the area associated with a z of 0.8? Okay. Now, based on this figure, should I subtract these or should I add these areas together? For the total area. So the total area, do you think I should add these two numbers together or should I subtract them? Add them because, yeah, it's getting bigger. So the total should be more than each individual one. So that's why you want to draw them so that you can make that observation instead of trying to remember, oh, if they're on opposite sides of the mean, blah, blah, blah. It's just easier to look at it. So you add those together. I'll do this myself. And so we get 0.596 or 59.6% of people have an IQ between 187 and 112. You're both leaving at the same time. Suspicious. Oh, is that what's going on? Okay. Yeah, it seemed kind of suspicious why you were both going. So another thing is if you randomly pick somebody from a representative population of the United States or whatever the world, you would have about a 60% probability that the person would have an IQ between those two values. I was going to make some comment about Trump voters, but I'll try to not say anything about that. Okay, you've got a couple of problems where they just give you the z-score. They give you the z-score. So it says find the percent area under normal curve between the mean and the given number of standard deviations from the mean. So when they say 1.08 standard deviations, that means that's the z-score. So a z-score of 1 means 1 standard deviation, less than the mean, -1. -2 z-score would mean 2 standard deviations less than the mean. So that's how you interpret z-score relative to this question of number of standard deviations. So to answer these problems, all you have to do is just take that number, the number of standard deviations, and use the positive value and look it up in your table. So just to give you guys some practice, so make sure you can confirm these are correct. So look on your table for 1.08, which is in the third column of Z numbers, or third column in the graph. I mean in the table. You should see 0.360, which then can be converted to percent. Okay, so this is using the table. Here they're asking for the area between these two values of z-score. So in this case, I'm going to draw my graph again, but rather than show it as values, I'm going to show it as z-scores. So how do I represent what's going on here? So before I would say this is where the mean is, but relative to z-scores, this is where z equals 0. So the z equals 0 at the mean value, and therefore these two are both to the right-hand side. This is 1.4, which is on the right-hand side, and this is, and I guess I should actually have this thing centered around the origin. So I'm going to, I was going to do that. There we go. So when you talk about z-scores, you actually, the distribution would be around the 0 point. So let me move this over here. So there's z equals 0. Z equals 1.41 would be to the right, and then you go a little further, that would be 1.83. So when we're dealing with the values and we're drawing this picture, it depends upon where the mean is. Usually it's positive, so we can draw like this. If you drew a curve when looking at just z-scores, it would be better to center it around z equals 0. So this is 0 on the x-axis. So they're looking at for between these two values. So remember, these z-scores will give you areas which are from the mean. So I could, if I make this green, I'll put a little green line under it, the area associated with a z-score of 1.41 would be that. And let's use blue for this one. For a z-score of 1.83, that's going to be the same area here plus that little bit more to get you to 1.83. So you can see that we're going to need to subtract the area associated with this z-score from the area associated with this z-score. So look up on your table. What is the area associated with z equals 1.41, and what is the area associated with the z equals 1.83? So I'm going to ask Harmony online to give me the answer. Hopefully she has her book. What is the area associated with the z-score of 1.41? So she says it's 0.421. Does everybody agree with that? It looks right to me. So this is 0.421. The next one should be higher because the z is a further out. So let's ask who else is online today. So Adriana, what is the area associated with the z of 1.83? You don't have your book. Okay. Let me show you the table. So I'm going to bring the table up for you. So here it is. What did I say it was? What's the z-score? There's the baby. What was it? 1.83. Okay. So 1.83 is on the table now. So look at the table on the left-hand side and tell me what the corresponding area is. So let's see if she's gotten an answer. Oh, you don't know. Okay. So what you do is you come down this column to 1.83, and then you go over to the right. So it's 0.466. So let me ask Adrienne if she hasn't. Do you see now? Okay, good. So it's 0.466. Oh, maybe again. 0.466. So it's 0.466. Because I'm looking for the red area, I'm going to subtract the green area from the blue area. So if I take the difference in those two values, you're like, which one do I subtract? Well, it doesn't really matter because you always have to end up with a positive area, so it's the one that gives you the positive value. So if you subtract the wrong one, you'll get a negative number, and you'll say, oh, I made a mistake. I'll make that positive, or I'll go change what I did. So I take 0.466 minus 0.421, and I get 0.045, or 4.5%, which is the answer that we got over here. Okay, now what I want to do is just show you the assignment for the lab or for the project. So let me pull that up just to show you it's exactly what we're doing right now. So it's nothing. You should now be able to do the entire assignment if you haven't. Okay, so oh, by the way, if you end up with any issues in doing the project, what you can do is, what I would suggest is you come to the library during my office hours and open up your project, and then you can just come and see me and say, hey, I don't understand how to do this, and I'll just walk to your computer and I'll show you what you need to do. I had some student yesterday who did that. She just came to my office and said, hey, I'm having some trouble with the project. I said, are you working on it on the computer in the library? And she said, yes. So I went, and it was easy to fix. So I'm not going to work the whole thing for you, of course, but if you get some specific problems, I'm happy to help. So the project says, assuming a normal distribution, use a mean of 50 and the standard deviation calculated from the data. So the data, yours should be close to 5. You might be slightly different than 5, but it's close to 5. Calculate the probability of getting the next data point in the ranges outlined on the next page. So they're talking about probability. So the first one we should know the answer to, because the mean is 50. What's the probability of getting less than 50? 50% probability, or 0.5. Okay. Here we've got more than 55, so we draw a line here which is greater than the mean, and it's going to be this little tail pit, which is just what we did. So the one we just worked on would be an example that would go with this. Here's less than 51. Well, 51 is going to be here. So you're going to take 0.5, which is everything on this side, plus the little bit between 50 and 51. So you'll add 0.5 plus a little area that you'll get. So that's how that one works. Here you've got 2 that are on the same side, which is what we did earlier. We just did a second ago, except they're on the left side, but it's still the same procedure. You'll have, you draw a line here at 48, here at 46. You'll have this area right there, and you'll take the area associated with the lower z-score and subtract it from the one with the more positive z-score. These are on either side of the mean, so you'll add those together. These are on the same side of the mean, so you'll subtract, but they're on the upper side instead of the lower side of the mean. And then the final one is less than 48, so it's just like the one we just did, except it's on the lower tail instead of the upper tail. So that's all you have to do. So and what I want you to do in this case is I want you to draw the lines associated with what they're asking. And then you fill in the area. You don't have to show the 2 areas that you're subtracting or adding. I just want you to show me the area represented by what the question is asking in the problem. And once you do that, then you can calculate the z-scores, appropriate z-scores, then find the areas, and either add them together, subtract them, add them to 0.5, subtract them from 0.5, depending upon what the area that you're looking at is involved. And if you have any, if you get stuck on one, just come and see me and I'll explain it. But you'll also have, there's that video that pretty much goes through every one of these scenarios again. So if you need to see it again beyond what we did today, there's also those resources if you're at home and you can't come see it. So that should be pretty straightforward. The key thing is to use your standard deviation, but 50 as the mean. Okay, so the next thing we're going to do is we're going to I'm going to skip ahead a little bit. We'll come back to these in just a second, but just wanted to show you how you might use this information if you actually were working in a job, quality control job. So this is problem 28, and there's some more, 28, 9, and 30. So there's a light bulb company which has a light bulb which averages 600 hours. So this is not an LED or a compact fluorescent. It has an average life of 600 hours with a standard deviation of 50 hours. So the mean is 600, the standard deviation is 50. The length of the light of the bulb can be closely approximated by a normal curve. A warehouse manager buys and installs 10,000 such bulbs. Find the total number that can be expected to last each amount of time. So they're asking between 600 and 675 hours. So again, we're going to draw a picture of what this looks like. And because it's not z-scores, it's actually numbers, the normal distribution is going to look something like that. Just want to check something. Yeah, I am recording. Thank goodness. Okay, so here's my normal distribution. Again, it doesn't have to be perfect or to scale. So the mean is 600. So I mark 600. I mark 675. I draw vertical lines for both cases, and then I fill in the area. So I need to find that area. Because it's going from the mean to some value, I don't have to subtract or add anything. I just have to do one calculation. So what I would do is I would say, what's the z-score associated with 675? I don't have to worry about this because the z-score of that is 0. So the z-score is going to be the x value, 675 minus the mean, divided by the standard deviation. So in our case, the value is 675. The mean is 600. I divide by the standard deviation. I'll get 75 divided by 50, which is 1.5. So that's my z-score. Then we go to our table, and we look for a z-score of 1.5. So Taylor, what is the area on this sheet of paper for a z-score of 1.5? Yep, good. Okay, so the area associated with the z of 1.5 is 0.433. So 43.3% of the light bulbs will last between 600 and 675 hours. Or if you take the decimal equivalent, 0.433 times the number of light bulbs, 10,000, that's going to give you 4,330 bulbs. So out of the 10,000, 4,330 bulbs will last between 600 and 675 hours. And you know, with 10,000 light bulbs, that's a lot of light bulbs. So you're probably going to be pretty close to that. If you had 10 light bulbs, you know, then you could have, you know, you might have 6, or the chances of the probability of having away from this normal curve is going to be greater. So what might somebody how would you use this data besides just saying, well, that's interesting? If you were the warehouse manager and you had some or say in the school here, you've got all these light bulbs through the school, and you know that they last a certain amount of time. One thing you could do is you could say, well, maybe I should check these light bulbs out. And at what point, you wouldn't want to wait 1,000 hours to check the light bulbs out, because most of them would be burned out by then. But you don't want to check them after 100 hours, because the probability that anyone is burned out in 100 hours is pretty small. So you have to make some kind of judgment. You'd probably take the mean and go maybe 2 standard deviations less than the mean. And you'd have some kind of schedule. Make up a spreadsheet that has an alarm that says check these light bulbs after 500 hours or something like that. Whatever 2 times the standard deviation is. So yeah, it would be 500 hours would be two times less than standard deviation. And at that point, only 4%, approximately, actually 2.5% of the light bulbs will have burnt out. Which, that is probably small enough that it's annoying, but it's not critical. So that's how somebody might use this data. Set up a maintenance schedule. It's kind of like with if you're building an aircraft engine, and the parts are made out of aluminum because you want it to be lightweight. But aluminum has a tendency to stretch more so than steel does. And there's probably some material properties of aluminum that say after 10,000 hours of running that you have this probability. If you did a life analysis of that particular material, you might get a normal distribution that says on average they're going to last for 10,000 hours, and the standard deviation is some value. And again, you would probably set up an overhaul of the engine. You might want to replace certain blades. In that case, if a blade fails, that's really bad news. So light bulbs going out versus blades failing in a jet engine, there's a huge difference. And so you would choose a much larger multiple of the standard deviation and subtract that from the mean to do your maintenance stuff. So it all depends on how critical it is. Here, I have these airbag recalls, the Takata. You've heard. Does anybody ever check? Has anybody checked their car to see whether it has the bad? Yeah, yeah. If you don't know this, you can check the if you take your car VIN number and you go online and you enter the VIN number, it'll tell you whether there's an active recall. Because my wife's 2010 Civic, I thought they mentioned that year Civic had a recall for the airbag. So I called them up and they said, what's your VIN number? So I gave them the VIN number, and they said there weren't any recalls. So I didn't have to take it in, which was good. And then I did it myself because I just didn't trust them. So I went online and there were no recalls on that particular car. So that was good. But I don't know how that company's still in business. The number of fines and all the other. Yeah, that's the problem. Yeah, they're the only game in town. Yeah. So yeah, what happens when something like that happens? How do you keep this company afloat? What's that? Is that what it? Yeah. Okay, next one. Chickens. So we have weight of chickens, chicken farmers. So the chickens at Ben and Ann Rice's farm have a mean weight of 1,850 grams with a standard deviation of 150 grams. The weights of the chicken closely approximated by a normal curve. Find the percentage of all chickens having each weight. Okay, so there must be a second part to this because I don't see anything. Oh, well, I'm going to make something up here. So let's say between 1,650 grams and 1,790 grams. Is there anybody here who will only eat organic chicken? I buy that. There's the chicken breast at Food Lion. Oh, is anybody, maybe somebody online eating organic? No. Or does that answer your question? No, that was to something else. The family pack of chicken breasts at Food Lion, those things are huge. Oh, before they were genetically bred for the, they were a lot smaller. Yeah, I know. I feel a little bad about buying chickens that must have breasts that big, but $1.99 a pound for chickens. Okay, so you can see here's my mean, 1,850. Here's 1,790, which is less than the mean. Here's 1,650, which is less than the mean. We said if they're on the same side of the mean, either on the upper side or the lower side, then then you're going to subtract the areas that you would get associated with those. So we're going to calculate the z-score associated with 1,650, and we're going to calculate the z-score associated with 1,790. And remember, that's going to be x minus the mean divided by the standard deviation. In this particular case, the mean is 1,850, and the standard deviation is 150. So go ahead and calculate the z-scores there. See what you get. They should be both negative. Yeah, so you're doing all the calculations on the side there. No paper today. Oh, is that what's going on? Okay. Yeah, so what'd you get? Negative 1.3 something and negative 0.4. Okay. That sounds pretty decent, reasonable. Did anybody have corned beef and cabbage for St. Patrick's Day? Does anybody like corned beef and cabbage? Yeah? Cabbage is okay. Terrible looking what? Oh yeah. Yeah. Poor guy. Yeah, the guy, they can't catch a break, can they? They're just so, the crooked news media is just so picky about everything. Yeah, yeah, the head on a Guinness is an important thing. So there was the other one. Somebody said top of the morning to you, and apparently nobody says that in Ireland. It's just in movies. I don't know if that was the other. There was the other. I mean, I probably would have done the same thing. So I'm not going to profess to be an Irish. Okay, so what we get is z-score of 1,650 is negative 1.33, and the z-score associated with 1,790 is negative 0.4. So now we look at the corresponding areas, but using the positive values. So 1.33, and the area associated with 0.40. So we look down our column for z of 1.33, and we get 0.408. And for 0.4, we get 0.155. So the area, the net area here, I'll just say total area that we're interested, is going to be the larger number minus the smaller number, because they're on the same side of the mean. So we're going to subtract them. And we get 0.253. So 25.3% of their chickens have a weight between 1,650 grams and 1,790 grams. Yeah, if you buy those whole chickens, you know, you can buy the whole chickens. Those are 99 cents a pound on sale. Has anybody ever cooked one of those whole chickens? You make chicken salad? Yeah. I usually use the chicken breast for chicken salad. I put them, I boil them in water, and then I stick them in a food processor and shred them up into. But a lot of times we use the whole chickens for like soup. But there's, you know, those are probably more not so genetically weird chickens. You know, those are normal size, but it's amazing how less meat there is on one of those whole chickens than there are in those monster chicken breasts. Okay. Yeah. I know. I'm not sure if I want to know. Okay. The last practical example here is it's a cereal box, and it's in 24-ounce boxes. The machine that fills the boxes is set so that on average the box contains 24.5 ounces. The machine-filled boxes have contents weights that can be closely approximated by normal curve. What percentage of the boxes will be underweight if the standard deviation is as follows? So what they're going to do is you know, it's like, you know, when you go in a store and somebody accidentally gives you more change than you're supposed to get. You know, you don't normally notice that. You might not say something or whatever. You know, you don't go back and say, "Hey, I'm giving you money back." You're like, "Oh, that's great." But if they give you less money than you expect, then you're definitely catch that and you'll come back and complain. So the same thing with cereal boxes. So even though it says 24 ounces, they're going to overfill it a little bit, because they wouldn't want, if they just did 24 on average, half the people would get less than 24 ounces and they'd feel like they were cheated. So you got to give them a little more so that a small enough percentage has less than the 24 that they wouldn't start some campaign and a class action lawsuit about you know, getting cheated on their cereal box stuff. So let's see if we can just see what this means by drawing a picture again. So we draw our normal distribution. So it says that certain dry cereal is packaged in 24-ounce boxes. The machine that fills the boxes is set so an average, so the mean is 24.5. So this is 24.5. What percentage of boxes will be underweight if the standard deviation is follows? So what we do is we look at we put 24 ounces here, which is what's on the box. These are the underweight ones. So some small, some less than, you know, it's going to be less than 50%, because if the label of the box and the target were the same, then you'd have 50%. So it's going to be less than 50%. So this is one where you're going to find the area between here and there, and you're going to subtract it from 0.5, which is the total area between the mean and everything to the one side or to the other side. So by reading the problem, we've figured out what they're looking for is that area, and once we have that, then the rest of it's just a normal problem. We know that x bar is 24.5. We know the standard deviation is 0.3 ounces. So these are ounces. So what we do is we find the corresponding z-score to 24, which is the limit that sets where underweight is. So the z-score associated with 24 is going to be 24 minus 24.5 divided by the standard deviation. So you're going to have negative 0.5 divided by 0.3, which is negative 1.67. So that's the z-score that I'm going to use to find this area. And then I'm going to subtract that from 0.5 to find the area there. So let's just make a red crosshatch here. So that's the area that the curve is giving me, is that area. So the area associated with the z-score of, and I'm going to use positive 1.67 because the table doesn't go to negative. So I look up the area associated with z of 1.67, I get 0.453. So the area, the black area here, is equal to 0.5 minus the red area. So you get 0.5 minus 0.453, which is 0.047. So 4.7% of the boxes will be underweight. And the only way you can reduce that number is to increase well, there's two ways you can do that. You could have a more accurate filling line. But, filling things like cereal boxes, I mean, how do you do that? Do you have a chute that opens up for a certain amount of time? And you figured out that, if I leave it open for 2 seconds, it'll put down 24.5, but, opening, closing the chute and all kinds of other factors are going to make it so that it doesn't always get you 24.5. You might have a scale underneath the cereal box. I'm not sure. Yeah, that could be. That's a good point. That might be how they work. I'm not sure. But then you got to make sure the box is under there when that chute opens. So, I mean, that's the whole. So actually making machines to fill cereal boxes seem kind of boring, but in some ways it's not so boring because you got all those interesting things like that. How do you do? Well, here's another story. The paper mill in Covington makes, one of their products is paper for flip-top cigarette boxes. Much less than they used to make, but they still make them. And the machines that are made to fill the packs are, they make them at a certain rate. And they are, I'm trying to remember now how fast it is, unbelievably fast. I'm trying to think if it's minutes, this many packs per minute or packs per second. It must be minutes. It's, yeah, it must be minutes. So I think what I remember, and it's been a long time since, I don't think, they're probably not that much different, but the cigarette packing machines would do 600 packs in a minute, which if you think about that, divide by 60, that's 10 packs per second. 1 pack per tenth of a second. So just going 1, you fill 10 cigarette packs. So you got to imagine, you got to take these, what you have is you have the, let me see if I can find some pictures here just to show you. But designing these cigarette filling machines that can actually pack cigarettes that quickly, you're like, this is kind of a, I'm not sure if I want to have a job designing cigarette packing machinery, but the the company that
Okay, so your attendance question for today relates to this topic of normal distributions. So we've mentioned that one of the measurements that has a normal distribution is the IQ test. And I want you to go into Wikipedia. So search under Google for the Flynn effect. So just give a sentence or two explanation of what the Flynn effect is. It's also interesting reading if you just look at some of the articles, the effect of sex on intelligence. Not whether you're having sex, but the sex of the person. And there are a lot of studies been done, and some say there is and some say there isn't. One of them says that males and females in mathematics have about the same average performance, but that the men have a higher variance, which means that they have more low scores but also more very high scores. So you get the really smart math people and the really dumb math people. So the average is still the same. But if you're looking at the high performers, the people doing research, there's just a larger pool to select from. Anyway, there's a lot of interesting stuff.
The companies that made them were German companies, which is not surprising, because the accuracy that you have to. So let's just show you this. Cigarette filling machines. Okay. So those are, yeah, they don't even have them. They probably don't show pictures of them because they're so proprietary, right? Yeah, yeah. So then they don't show them because it's all proprietary as far as how they. Here's one. So what you have is you have all these cigarettes, and then they come down into. So you've got them in kind of a general hopper shape, and then you have them come down into these little channels. And so the way it works is the cigarettes are put there, and then the wrapping paper is wrapped around it, and then the boxes are wrapped around the cigarettes. It's not like they don't form the pack first and stick if you've ever taken cigarettes out of a pack and tried to stick them back in there, they don't ever fit back in there. I don't smoke, but I've, in my job at Westvaco, you take one or two cigarettes out and you try to stick them back in there. It's like a cereal box too. You notice whenever they get the cereal box gets fatter, and you try to, okay, how do I get them so that the box is not so thin? Anyway, so they actually build the cigarette box around the cigarettes, and then they glue the seams, and one of the key things about making paper for cigarette packing machines is that the glue dries quickly enough so that when they come out the end of the machine, the glue's not going to fail and you have the pack fall apart. And one of the reasons they actually use the paper, you used to have the soft packs and they have the hard packs. The hard packs, even though the material to make the packs is a little more expensive, the you can run the machine so much faster. So the production rate overshadows the additional cost of the different kinds of cigarette packs. Now, this is a China cigarette packing machine. Let's see if we can find the other cigarette packing stuff here. Yeah, I wonder who makes these. Let's see who makes it. Like I said, they probably don't sell them out on the open market because they're such a proprietary thing. So I think I assigned this. Did I assign the homework for this section? I didn't. I've now assigned it. So what we'll do next time is we'll come back and we'll just finish up a few extra problems, but we'll definitely be moving on to chapter. We're going to move to do chapter 13 instead of I'm going to wait till the last minute to do algebra. So the next one is going to be personal finance. Yeah, just because I decided to hold off on it. Yeah, I know, but it's amazing how many people have forgotten their algebra. You'd be very disappointed, or you might not. I don't know if you'd be surprised, but yeah, people do not do very well in algebra. So we're going to do that as the last thing. This next thing will be personal finance, which actually is pretty interesting and very useful. So.